About electrophilic aromatic substitution reactions. And the first reaction that I think is important is called halogenation. Halogenation. And what you start off with is a generalized overview of this reaction. You obviously have a benzene ring. These all are reactions with benzene or really any aromatic compound. That is a horrible drawing. There's a hydrogen there. We go ahead and react that with, and I'll switch colors too. Go ahead and label this any type of a halogen, chlorine or bromine usually, because those are the only ones that we can use at this point. And an iron tri whatever version of that halogen. And what you get as a product though, if I could find my color there. So the product of these reactions, of halogenation reactions via electrophilic aromatic substitution mechanisms, is you are substituting that H with a halogen, and that's really helpful because halogens are really lots of other things that we can add to this. So in this reaction, and I'll draw a generalized overview of each and every one of them, but in this reaction, the electrophile, oh, I don't know why that is so crazy. And the electrophile is always going to be a positively charged chlorine or a positively charged bromine. The next reaction that I wanted to talk about, I'll go ahead and circle this halogenation reaction, is nitration. A nitration reaction. So just like the previous one, I start off with a benzene group. I do some type of a reaction, and I'm going to have attached to me a nitro group attached to it. How do I get that nitro group attached? Well, I add HNO3 and H2SO4. Now, every single one of these reactions, I don't know if I mentioned this, every one of these reactions is ran under acidic conditions, and there will be consequences of that later. So the next reaction is sulfonation. And I'm going to go ahead and just draw that reaction out as well. We have, of course, a benzene ring. You figured I'd be better at drawing benzene rings with this pen by now, but anyways, and through some type of a reaction, we are going to add hold on, let me finish drawing this. To this, we add a SO3H, and I'll draw all the mechanisms for each and every one of these later, but you add SO3 and H2SO4. Generally speaking, if you're not working with H2SO4, you're working with a Lewis acid, usually iron or aluminum. Trihalogen. Okay, so that's sulfonation. And then the last type of reaction that I'm wanting to talk about are called Friedel-Crafts reactions. I think it's hyphen actually. Friedel-Crafts reactions. And there's two types of Friedel-Crafts reactions. There's Friedel-Crafts alkylation and Friedel-Crafts acetylation. And then there's alkylation. Well, obviously by the names, one of these adds an acetyl group, the other one is going to add an alkyl group. So I'll just go ahead and draw the overall mechanism for this. So you obviously have an aromatic compound, benzene, being the poster child that it is, and it's going to give us some type of a reaction. And what we do in this, we add, let's see if I can try to fit this in a very small amount of space. I'm going to draw it like this. There's a carbon. We're adding a keto group and then the rest of the molecule to that. What are the reactants that we need? Well, we need that R. We need our keto group. And usually an acid chloride. I don't think you can do that with Br. Maybe you can. And then aluminum trichloride. Again, Lewis acid. Not Lewis acid, but all acidic conditions. And this is really useful for a lot of other reasons, which we'll talk about later. So that's acetylation. Alkylation, though, well, for alkylation there's actually Well, there's other ways that you can do this, but I'm just going to go ahead and stick with what my outline shows. And so you have a benzene there. We're going to react that, and the substituent of that is going to be, whoa, see if I can fit this there. Your substituent is going to be, I think I've been sticking with that, is just a carbon group, a long carbon chain. So what you have here to get that is a R and then a chlorine. I don't know if it can work with bromine. I would imagine it would. And then aluminum trichloride. And we'll go ahead and we'll talk in great detail about the mechanism and the specificities of this reaction here. So these are the reactions, the 5 reactions that you need to know. There's halogenation, nitration, sulfonation, Friedel-Crafts acetylation, and Friedel-Crafts alkylation. And then I'll go ahead and label the electrophile in this group, and in this one, the electrophile, that's my generic substitution for that, is NO2 plus. For sulfonation, my electrophile is SO3H plus. For Friedel-Crafts alkylation and acetylation, well, for the acetylation, my electrophile is a RCO, positively charged there. Kind of hard whenever you think about it. I don't know how you can see that. And then for this, my electrophile is just a carbocation, really. But I just want to make a note that, and I don't know if I should write this out, but okay, so we have H2SO4 is the only acid that we're going to use for this reaction, the only strong acid that we're going to use for this reaction. The other acids that we use, because these are all under acidic conditions. So these two here, the FeX3, or iron trichloride or iron tribromide, should be a Br there, sorry, or the aluminum trichloride, these are all Lewis acids with that MTP orbital, and we'll go ahead and divulge into each of those later, but those are the 5 reactions, that you need to know for this course. This is a electrophilic aromatic substitution mechanism for halogenation. We know what we're going over. We start off with a benzene, or an aromatic compound. It doesn't have to be benzene. Benzene is the poster child, however, for this. We go ahead and say we add Br2, and it could be chlorine as well, and then FeBr3. And what we're doing through this, and I'm just going to draw a hydrogen there so that it's more easy to visualize. You're substituting that hydrogen with either a bromine or a chlorine. And so what we get out of this is a bromine attached to a benzene group. So there's 2 steps that this is going to happen in, and I'm going to go ahead and color coordinate those. The first step you want to do, step number 1, is to create a leaving group or a electrophile. And the reason why I'm saying this is because they're often kind of used synonymous. So that's the first step that we're going to. So what we have here is, I'm just going to draw that out. We have a bromine here. We have a bromine there. I'm just going to draw a lone pair there. And then we have iron tribromide. Br, Br, and Br. And lo and behold, what do you think is going to happen? There's this MTP orbital. This is a Lewis acid. It's going to attach itself there. They're going to react. And what you get out of this is, and I'll see if I can draw the next step from this, is you have a bromine here with a bromine, positively formal charged, and I'm just going to write this out as FeBr3, but negative formal charge. And this right here, this is your kick-ass leaving group. This is what will drive this reaction so well. It's not the benzene. We got to remember those pi bonds in benzene are super, super stable. So we need something that's really unstable to react with that. And then, so that's the first step. The second step in your reaction is just generalize substitution. So I'll see if I can fit this all on the same page. So we have a benzene here. It's just floating around in our mixture. There's a hydrogen attached to that. And then over here lo and behold, comes, I'm just trying to switch colors here, that molecule down there. There's the Br, and then Fe, Br3. This has a positive charge, this has a negative charge, and I'll do the electron pushing arrows in gold. I know I'm getting kind of messy over there, but I'm just going to make a note that there is also, let's draw that out, yeah. So this pi bond here comes after, it's attracted to the positive charge on that bromine. If you're wondering why it's coming after this, draw the Lewis structures, and maybe that'll help you understand that a little bit better. And this is going to come over and to put itself onto that bromine with a positive formal charge, so that it will lose its positive formal charge. And what we get out of this reaction is, and I want to make a note that this is very, very slow, because you're disrupting aromaticity. You get out of this is a carbocation there. There's still a hydrogen there, but we've had something new attached to it. What we have now attached to it is a Br group. Okay, so what we get out of this reaction over here is just a FeBr4. This still has a negative formal charge though. This in this form is a Lewis acid. Now it's got a negative charge. Well, as you may have guessed, this is getting kind of messy, but this negative formal charge is going to come in and it's going to deprotonate that benzene ring. And what this does, the only reason that we do this though, is because this reaction is going to happen super, super fast. Because when you pluck that proton off and that lone pair goes back in, you have restored aromaticity. So if you're restoring aromaticity, this reaction is going to happen in super fast, with super fast rates. And what you have attached to yourself is a bromo group or bromine group. And that's your product. I didn't mention that I felt like was important to mention though, is that whenever you're doing a reaction like this, and this is a common mistake that people make, is you say you've already done the whole electrophilic reaction. I'm just going to say this is E as your generic symbol for that. And you have your conjugate base from one of those Lewis acids, or from one of the acids that we ran, because this reaction was ran under very acidic conditions. This pair here will never, ever, 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 never, never, never attack that carbocation there. And I know that you're thinking, well, I mean, it's a positive charge. The carbocation has a positive charge. That Lewis acid, I'm sorry, the conjugate base, wow, from your Lewis acid has a negative charge. Why wouldn't we do this? Why wouldn't we have something like this? Because this compound here is not aromatic. This is not an aromatic compound. And aromatic compounds are way more stable. You want to make aromatic compounds. So this reaction here, this reaction will never in a billion years, and this will never take place. Also, when you have this carbocation here as the reaction intermediate, one of the things also that I forgot to mention is that this will give us at least three, depending on what substituents you have. You may have more. So I'm going to say 3 or more resonance structures. All right, so 3 more resonance structures can be formed by that.